So thank you for coming to my talk. My name is Paul Anderson. I'm VP of Engineering at Tech. I've been working on static analysis tools for more than 20 years. What I'm going to be talking about today is finding serious bugs with advanced static analysis. So let me get stuck in here. So here's the key takeaway, which is that real functional safety is more important than conformance. Now, by conformance, what I mean is conformance with coding standards. Now, we're probably all familiar with coding standards such as MISRA or corporate coding standards and so on. And they're great in the sense that they certainly reduce the risk of writing code that has bugs in it, but they're not necessarily a guarantee that you will prevent bugs from working their way into your code. So I'm not here to denigrate or to reduce the importance of coding standards. They are very important, but the fact remains that even if you are 100% conformant with any coding standard, you may still have bugs. And what really matters is functional safety rather than dogmatic conformance. So this is the message that I hope you will all go home with today, that real functional safety is more important than conformance. Okay, so here's an overview of what I'll talk about. So first of all, I'll give a very brief introduction to static analysis, and in particular the differences between superficial static analysis and deep static analysis. I'll talk about the risks of C and C++, which are really what make these kinds of tools pretty important. Then I'll talk about techniques for advanced static analysis, and then the bulk of the talk is where we'll go into a few examples of bugs that showed up in code. All of these bugs showed up in real code, production code that had undergone some validation and testing already, none of which are really plausibly detectable by any tool that is focused only on establishing conformance with coding standards. That is, most of this code is pretty much conformant, or at least the bugs that were detected by the advanced static analysis tool would not have been detected by a pure conformance testing tool. And then at the end, I'll talk a little bit about customization. Okay, so static analysis. So what does it mean? So I apologize if I'm repeating things that people already know, but let me just describe what I mean by static analysis. So static analysis is any technique that computes a property of code without actually executing it. In contrast to dynamic analysis, which always involves executing code, static analysis is a technique that looks at the code and computes properties of it without actually doing any form of execution whatsoever. And as a consequence of that, you don't need test cases. So in principle, static analysis can find things much more easily than testing. So you don't have to put in a lot of effort to construct test cases in order to get the benefit of static analysis. It's usually this two-phase process where the analysis creates what we call a model of the code. I'll say more about that later. And then extracts information from that model in various ways. Now, this talk is mostly about advanced static analysis for bug finding. There are other forms of static analysis that allow you to compute other properties, but this is really about bug finding. That is, the tools that are capable of hunting for bugs, but not necessarily guaranteeing that there are no bugs in your code. They're not proving tools. They do not prove correctness, but they are nevertheless good at finding bugs. And the example tool that I work on is Code Sonar, and it is very typical of this class of tools. Much of what I will say is applicable to other advanced static analysis tools, but of course, we promote Code Sonar because we think that has pretty good properties. Okay, so there are, roughly speaking, two kinds of static analysis. There is the superficial and the deep. So let's talk about what those are. So superficial static analysis is good at finding violations of syntactic properties. So syntactic rules are typically the things that are mostly found in coding standards. They're mostly surface level properties. They have to do with things like naming conventions and use of certain constructs. They're often about improving readability to make it easier to maintain the code and for people to understand it. And as a consequence of their superficiality, they are generally fairly easy to find with even simple static analysis tools. Unfortunately, they do not have a very good direct correlation with serious defects. So I cite this paper you can see on the right from 2008 that showed that only 9 of the rules were better than random at predicting whether or not code contained defects. Now, like I said earlier, I'm not here to denigrate coding standards like MISRA and so on. They are very useful. They do certainly reduce the risk, but they don't guarantee to find bugs that are most of the serious bugs. They're for reducing the risk of bugs, but they're not necessarily good at finding bugs. Now, the other form of static analysis is a deep static analysis, and that's designed to find violations of semantic rules. Now, these are mostly about runtime properties of the code, such as whether it encounters undefined behavior, which we'll say a bit more about later. The key thing about these rules is that they have a very high correlation with serious defects. So most of the serious bugs that C and C++ programs are vulnerable to correspond to these kinds of semantic properties. Things like buffer overruns, data races, use of uninitialized memory, dereferencing invalid pointers, and so on. And these defects are only covered indirectly by MISRA rules. So there is one MISRA rule that says no undefined or unspecified behavior, and that really is all they say about these kinds of defects. Now let's talk a little bit about the risks of C and C++. So I mentioned undefined behavior before. This is the Achilles heel, the fatal weakness of C programs especially, and lesser so, but still there with C++ programs. The key thing about undefined behavior is that when it's encountered, anything can happen. There are no guarantees. This is often referred to as the catch-fire semantics of the language, because the language is legally within its rights allowed to set your computer on fire. Now, of course, that doesn't happen. What happens is that compilers have to make assumptions that there are no undefined behaviors in your program, and that can lead to problems. This is not a rare thing. Most programs that have bugs have some form of undefined behavior in them. And they correspond very strongly to the serious bugs that I mentioned earlier, such as what I've listed here. So given that the semantic deep static analysis is difficult, let's just talk a little bit about the kinds of techniques that are necessary in order to find those things. So, so again, just a reminder, what I'm talking about here are advanced static analysis tools whose primary purpose is to find these serious bugs. Now, these serious bugs are mostly undefined behavior. And so the way the tools work is they take the source code, they parse the source code, they create a set of intermediate representations, and then these tools, they do what's called an abstract interpretation of the code, or really the intermediate representations, in order to reason about the possible ways in which the code can execute. Now, this abstract interpretation technique is, there are a variety of different ways it can happen. Most of them are based on some of the techniques that were used in high assurance hardware design, such as model checking and the like. These tools are also aware of APIs, so they know when misuse of an API happens and can flag defects based on that. So the key properties are the following. So first of all, the tools do a precise whole program model creation. So what this means is that they start with parsing the code in exactly the same way the compiler parses the code, and they create the model that I mentioned earlier, which is consisting of things like control flow graphs and call graphs and cross-reference information and so on. And this allows the analysis to do the various semantic searches in order to find the bugs. So the searches, the algorithms, there's flow sensitive, meaning they do a kind of data flow analysis. They're interprocedural, meaning the analysis can cross procedure boundaries. They're context sensitive, meaning that different calls to the same function in different places can have different semantics. Their whole program, meaning that they can track the effect of the execution of the code across compilation unit boundaries as well. And they're path sensitive, meaning that they explore the paths through the program and compute the properties of the abstract state of the program along each path individually. And what this means is when you get a result back, it can show you the path through the code that must be taken in order for that to happen. Then they are concurrency sensitive, meaning they understand threading APIs and locking APIs and how they interact, so they can find really serious problems such as data races that I'll explain later. And finally, they typically do a little bit of statistical analysis, sometimes based on machine learning. And what that's useful for is finding places where the code deviates from what is considered to be normal. And we find that code that is deviant in that sense is often very highly correlated with real bugs. And I'll show you a good example of that later. All right, so now let's get into the meat of the talk, which is about these examples. The important thing about these examples is that they were all found in production code. That is code that was released, that was running on various machines, and they had not been detected by any of the QA activities of the organization that was producing the code. And another key property of them is that they're all are unlikely to have been flagged as violations of coding standards by any tool. All right, so let's look at this first one. This is a pretty simple function, and it's interesting from a couple of perspectives. So first of all, it illustrates that just how easy it is to make very serious mistakes in C and C++ code. And secondly, it indicates that, well, when I show you the result, it shows you how the static analysis can do this path-sensitive exploration of the program and find bug fairly easily. So I'm betting that most people who look at this code are not able to spot where the problem is very easily, because the code is a little bit idiomatic. It's using string manipulation functions like strlen and strcat. It's using malloc. And it's using those in a combination that looks on the surface to be fairly mundane and fairly routine. But unfortunately, the programmer has made a typographical error. And that has meant that there is a buffer overrun in this code. Now, the amusing thing about the code is the comment that states baldly that there are no buffer overflow vulnerabilities, but in fact, the programmer made the mistake, and so there is a buffer overrun vulnerability. So let me show you in this next slide what CodeSonar produces when it analyzes that code. So what you see here is the path through the code that must be taken in order for this bug to happen. So on line 2186, execution enters the function. On line 2192, the true branch of that conditional is taken. Then there's a malloc on the following line, and then on the last line that's shown there is the buffer overrun. So all this text that you see there is automatically generated by the tool to explain the reasoning that it used in order to conclude that there was a bug on this line. And what you can see there is it's saying that the buffer that's being overflowed is newlock, and it gets its value from the malloc on the previous line. So if you look closely at that malloc, you'll see where the bug is right there. So in C, when you're copying strings into newly allocated memory, what you do is you allocate 1 byte for each character in the string. You add 1 to that number in order to allow for the null terminator, and you allocate that amount. And that's what the programmer intended to do, but he made a mistake. He put the +1 outside the parentheses instead of between the 2 parentheses, and as a consequence of that, the allocation allocates 1 too few bytes, and then the result is it has 1 added to it, which advances the pointer to the next byte. So when the stir copy comes along, it copies into the wrong point in memory, overflows the buffer by 2 bytes. Now, buffer overruns are undefined behavior. So as a consequence of this, who knows what might happen? It could be that the code executes just fine and nothing happens because it happens to overflow into some spare memory that's not used by anything else. Or it could be overwriting some other buffer, or it could be destroying the data structures that malloc uses in order to manage the heap, in which case, who knows what can happen. So in any case, if you're lucky, it will crash right away. If you're unlucky, it will silently corrupt some data, and you won't notice the effect of that until much later. Okay, let's move on to this next example. So this is a pretty cute example as well, because it illustrates, again, a very easy mistake that can be made in C and C++ programs. In fact, you can make this mistake in pretty much any programming language, but in C and C++, you can be a little bit more vulnerable to it. So everybody who's ever programmed has done copy-paste at one point in their lives. This is where you're doing something with one variable, let's say, and you need to do something very similar to another variable, and so you copy the original and you change the copy to adapt it to the new location, and hopefully, because the original has been tested well, that the copy will work just as well as the original. It's not a great programming technique. It's much better to abstract these things into functions or templates or whatever, but nevertheless, copy-paste is abundant. Copy-paste errors occur when the user attempts to make the change in the copy, but makes a mistake. Typically, it's a mistake that means that one of the changes that should have been made wasn't made. And as you can see, by staring at this code, it can be very, very difficult to spot where that mistake was made. But the static analysis finds it right away. So you can see here the report from CodeCenter that finds this copy-paste error. And so on the right there, it is identified that that function more arrays is a copy of more variables, and it is noticed that in all places where there was v count, in the first it was changed to a count, except for that last one, which was missed. So as a consequence of this, the initialization code, starting at line 176 there, is going to not initialize that array properly, unless the value of v count and the value of a count happen to be exactly the same. And who knows if that's plausible or not. In any case, what this can result in is either not initializing enough of that array, or possibly even overflowing the array and causing, again, undefined behavior. So this next example has to do with concurrency analysis. So this is a data race. So let me explain data races to you. Probably most people are at least in principle familiar with what a data race is, but the definition of it is quite precise. So A data race occurs when there's more than one thread of execution. Those threads are accessing some shared resource. In this case, it's a shared memory, like a variable, which is just shared between the threads, a global variable in this case. And at least one of those accesses is a write. It is changing the value of that variable or potentially changing the value of the variable. And finally, there's no protection against concurrent access to that variable. And by that I mean locks. So data races are extremely hazardous in C programs for several reasons. So first of all, it's really easy to make the mistake of missing a lock, and there's nothing fundamental in the language that will help you find that you've missed it. So it will get through your compiler just fine. Because remember that concurrency itself is not built into C. You have to use a threading library in order to get it. So the other reason that data races are very hazardous is because they are highly non-deterministic. So you can run your program 1,000 times and it will run just perfectly well because you don't happen to hit the exact sequence of instructions that triggers the bug. And then on the next time you run it, it can fail miserably. And failure modes for data races are typically very, very mysterious. So they don't cause a crash right away. It would be much better if they did cause a crash right away because then you'd know about them very quickly. What they typically do is silently corrupt the value of a variable so that it no longer makes sense. They end up, and the consequences of that you may not notice until very much later. So the symptom of the bug may be very far removed from the cause, and that's going to make for a very difficult debugging scenario, especially because you may run the program dozens and dozens of times and you may not hit the particular interleaving of instructions that gives rise to the corruption of the variable. Data races in C are, of course, undefined behavior as well. So as a consequence, you have to get rid of them. So what you're seeing here is the report from CodeCenter that finds the data race. So on the left, you've got code that changes the value of the variable called flags. You can see that macro has been expanded to indicate where the that on line 158 there, you can see that the value is being ORed into the variable. And so that's your write. And notice there's no locks there. And on the right-hand side of the screen, there is the read from the variable. So that is reading the variable flags. It's doing an AND against it. And again, there's no lock. There's no use of a mutex or whatever to prevent both of these threads from concurrently getting the value of the variable. So in order to find this, what CodeCenter had to know, first of all, was that there are entry points to threads. So both end search on the left and input func on the right are entry points to threads. And so it has reasoned about the thread execution. It has concluded that these threads can execute concurrently. It knows that they are manipulating variables, that flags variable in particular, and it doesn't see any lock functions along the path there. So as a consequence, it concludes it's a data race. Yeah, like I said, data races are undefined behavior, and they're particularly tricky because programmers are very prone to persuading themselves that some data races are okay and some data races are benign. That is categorically false. There is no such thing as a benign data race. And the reason why is this. Compilers must assume that there is no undefined behavior in your program. And as a consequence, they must assume that there's no data races. So they, in order to do optimization, they feel free to potentially reorder the execution of instructions in your program in order to get better better performance or whatever. And that reordering can upend some of the assumptions that the programmer might have made about whether things should be executed in a particular way. And I can point you at papers that describe this in more detail if you like. This next example is deviant behavior detection. So I mentioned earlier that one of the techniques that these advanced static analysis tools use is a statistical analysis of the code, often driven by machine learning, which is targeted at finding deviations from what's apparently normal. And one of the deviations that we find here is in the use of a return value from a call to a function. So, so this is an ignored return value report. Now, CodeCenter is capable of finding these for basically any function, so you can tell it. Make sure that if you call, say, a function open, that you always use the return value from that function, either to make sure that it doesn't leak, or maybe to detect that there was an error in that. Although it comes out of the box capable of finding lots of these things, it also has this built-in functionality where it will look at your code and look at the functions and figure out that most of the time you are checking the return value of a function, and if there are any places where you're not checking the return value of the same function, that those should be tagged as anomalies and therefore reported as potential bugs. So in this case, so line 48 there, we've got a call to get file, get URI. And that value is returned and placed in the variable called URI. And the explanation there explains the reasoning. So it says that in more than 98% of the time across a large number of code bases, we have seen that the return value from that function is used. So the fact that you don't use it along this is possibly indicative of a bug. So it's an anomaly, and anomalies correlate very well with bugs. And so the curious thing about this is that, so you see I've highlighted that variable URI. You can see later on that in fact the variable is used, but the key point here is that it's not used along this path. So after the function is called, execution proceeds to line 56, and that seems to be some kind of error condition. I have some bubbles here that explain this. So that's some kind of unusual condition that forces an early exit from the function, and as a consequence of that, the value is not used. Now, it could be harmless. It could be a value that you can discard at will, but it could also be a value that is maybe a buffer. So the type of it is G star, so this could be a leak as well as being a return and an ignored return value. So now this next example illustrates a very interesting property of CodeCenter and tools that can do what we call taint analysis, which is also known as hazardous information flow. This is one of my favorite examples to show because it's not actually a bug. It is intentional behavior, but it's intentional behavior that the people who are writing this program, the people responsible for this program, did not want. And I'll explain why. So this is a IRC server. So IRC, Internet Relay Chat. That is a program that is run on typically on the internet. People connect with their IRC clients. Probably most of you have used IRC clients at some point in your life. So you connect to the client, and the server is responsible for taking input from the client in the form of messages and then displaying those messages to other users through their clients. So it's fairly simple, but because IRC servers operate in a really hazardous environment, that is the internet. Any security vulnerability in this code should be considered to be extremely serious, because if there is a security vulnerability, then it may allow an attacker to take control of the server on which this program is running and execute their own code with the same privileges of that server. And that could do things like steal credentials, spy on users, and so on. The typical set of hazards that you might be vulnerable to. So what this warning is, what CodeCenter has found is a command injection vulnerability. So a command injection vulnerability is one where the text that is coming from across some channel, where that channel is not trusted, is being executed in some way. So, so let's dig into this a little bit further. So the first thing to notice is that on line 1436, you've got a macro there, debug3 log, and that expands to debug3 do log system. And what that expands to is a call to the function named system. And if you know the C library, you will recognize that function. It takes as its argument a string. It will spawn a shell, and it will execute that string within that shell. So there's your command injection vulnerability, because the value that's being passed into that is a read buff. And we can tell by looking at read buff that by tracing its value back to line 1422, that's the data that that is taken from the client. So the client has typed some data, and that ends up being executed as a shell. So the next thing you might ask is, well, under what circumstances will it be executed? So you see that memcomp on line 1435. It's looking at the first two characters of the read buff and the string debug mode 3 info, and that's just the constant string AB. So consequently, if an attacker comes along and types AB semicolon and then some code, that code is going to be run as the with the same privileges as the server. And of course, at that point, it's game over. The bad guys have won. They've gotten control of your system, and you've been owned. So you may ask, well, what was all this other stuff around here? What was this debug mode 3 and debug 3 log? What were they? Well, the fact is that this code was deliberately inserted by a malicious insider, and it was disguised to look as if it was completely harmless. There are probably other places in this code where you have if-defs that turn on and off different debugging functionality. So to a reader of this code, a casual reader who was only interested in looking for security vulnerabilities in production code, they probably made the assumption, or they probably would have made the assumption that debug mode was not turned on in production mode. Therefore, this code didn't necessarily need any deep scrutiny. Well, the attackers took advantage of that assumption and were able to insert this code and successfully deploy this backdoor into the server on probably thousands, if not tens of thousands, of these servers. This code did make it into the code base, and it was there for about 9 or 10 months, apparently, before it was found and before somebody raised the alarm and had it removed. Now, what this illustrates, though, in terms of the advanced static analysis, is that it's capable of doing this taint analysis. So that was key to finding this problem. When a program executes, it typically takes input from a number of sources. And usually, some of those sources are trusted and some of them are not trusted. With an IRC server like this, you can be sure that the network traffic is going to be untrusted, but maybe the file system is trusted, or maybe the clock is trusted, or maybe the environment variables are trusted. So what the taint analysis does is identify the sources of that data and it can distinguish between either on its own or because you tell it which sources of data are trusted and which are not to be trusted. And then it can follow the flow of that information through the program to the point where the untrusted information might be used without having first been sanitized in some way. So you see the little red underlining there on line 1422 at the call to receive. So that indicates that the value that ends up in length is tainted by the network, and also the value that ends up in rebuff is tainted by the network, which is why the command injection vulnerability below is so hazardous. You can see there the second bullet point in that box at the bottom indicates rebuff is tainted by network data. So when you use CodeStunner to do this kind of thing, you can, of course, set it up so that you can define your own taint analysis. So if you have, say, a device that's reading from a port, and the inputs that are coming in that port are not to be trusted, well, you can tell CodeStunner as much, doing a little bit of modeling, and then it can do that taint analysis for you, and you can use it to find places where you don't want that tainted information to cause problems later. Okay, so that was my last example. And so now let's talk a little bit about customization. So customization is important for these tools because it allows you to dramatically increase the value you get from them. So out of the box, the tools have checkers for possibly hundreds of different properties, and they can range between things like coding standards through some of the deep semantic properties that I was talking about, or things in between. And all of those are things that are generically going to be useful for pretty much all code bases. But most code bases have intrinsic rules that the authors of those programs wish to have enforced across the entire code base. So if you've got a corporate coding standard, for example, out of the box, CodeStunner is not necessarily going to be able to check that, but you can extend it to allow it to check for those properties. Similarly, you might have temporal properties about your program, such as thing A must happen before thing B, or things must occur in an alternating order, for example. Or you might have properties that have to do with the program semantics. Like the value of this variable almost always has to be in this range. And you can code up checkers for these properties, even if they're checkers that are only good for one program. So let me describe how you might do that. And most of this applies to CodeStunner. Other tools do have various customization mechanisms, but this is mostly about CodeStunner. So the first thing you might do is make configuration changes. So CodeStunner has lots of ways in which you can configure it, and one of the ways is to take existing checkers and make them work in a new context. The best example of that is the set of checkers that have to do with allocating and deallocating resources, such as memory or graphics handles or whatever. If you have a protocol for allocating a resource and then deallocating it, that's similar to, say, opening a file and closing a file, or allocating some memory and deallocating some memory, then it's really easy to just make a configuration file change that will extend all those checkers, including leak checking, to those domain-specific resources. So if you do that, you not only get leak checking, but you get things like use after free, or double close, or double free, and things like that as well. So that's the easiest way of customizing. The next easiest way is to do a bit of API modeling. So every program uses APIs of some form or another, and out of the box, CodeStunner will come with checkers for standard APIs such as the C library and operating system libraries and so on. If you've got your own domain-specific library, then there are likely to be rules about how that API should be used, And it might be a temporal property, such as, A must happen before B. But it might also be a property such as, see if a variable has a certain value. The way you do this is you write code, and you can write it in line, so it's next to your regular code, that educates the static analysis about the key properties of the API. So it makes it fairly easy to write these checkers. It feels a little bit like you're writing a runtime check for the same property, and you end up writing things that look a little bit like asserts, but they're not dynamic asserts, meaning they're not going to cause a crash at runtime. They're static asserts. They are things that are detectable by the static analysis tool. The next thing you can do is to get access to that program model. So I mentioned that earlier. It contains things like the abstract syntax trees, call graphs, control flow graphs, and so on. And CodeStunner has an API that allows you to reason about those things. So you can traverse the entire control flow graph. There's pattern matching on abstract syntax trees. You can do lookups of names in the symbol tables and so on, and you can combine all these to find different properties. And there's an API for reporting warnings that might be detected as a consequence of what you find. This is really good for finding syntactic properties, like naming convention violation, but also if you forbade the usage of a particular construct. So you might say, for example, in this module, you're not allowed to use, you're not allowed to call a particular function. And you can do that with that, even though that function is allowed to be called from other locations. Then there are analysis visitors. So CodeStunner, when it does its core analyses, it's traversing over these representations in various ways. And you can piggyback your own analysis on those traversals. So what you do is you write callbacks. And so there's a callback, for example, that is invoked every time a procedure is visited. And you can then compute some property of that procedure and issue a warning or not. The most sophisticated of these checkers allows you to piggyback on the path traversal. So that is the basic interpretation of one statement after another. And you can even ask along that traversal if the values of the variables are in an appropriate range. And so it's good for finding properties of that form. And so if you get one of these static analysis tools, particularly CodeStunner, then it's definitely worthwhile doing this kind of customization. There are other forms of customization like tool integration and so on. You can do as well, but that's very context dependent. I think all users of static analysis tools can get benefit from doing this form of customization, where they are extending the tool to find properties of domain-specific interest. Okay, so this is my final meaningful slide, which is my conclusion slide. Again, I'm just flashing up the key takeaway there, which is that coding standards are important and all, and do use them, please, and check for violations and correct those violations, because doing so will make your code better, for sure. But on the other hand, do not assume that doing that will make your code perfect. There are still plenty of bugs that can escape conformance checking and may cause you grief further down the line. So in order to reduce the risk of those, we recommend that you use the advanced static analysis. I hope it persuaded you that it's capable of finding things that are outside the bounds of what's possible to find with just conformance. And with that, I think that's my last slide. So I think we're ready to go over to the other question and answer session, and I can take questions there.